Good morning. Thank you, Ira, for the introduction. I'm Tony Yu from NASA Goddard Space Flight Center. Today I'm going to give you an overview of the advancement of the laser system for the laser mission. I want to acknowledge my co-authors at NASA Goddard Space Flight Center, as well as industry partners from BAE, Alpha Photonics, and Fibertech, and many more. So this is outline of my talk. First, a brief introduction of the requirements, how we flow down to the laser head, the frequency reference system, the power monitor, and a quick summary. The laser requirements, there's a poster actually in tomorrow to talk about the systems engineering approach on NASA's side and how we deal with the large amount of requirements flowing down through the science and the mission level. And this is also how the science and the mission and the space segment requirements flow down to the laser IRD that's captured all of the laser system requirements that we use for our design. And these requirements drove the design of one of the quietest spaceborne lasers to date. First, an overview of the terminologies. You have 3 spacecraft, and on each of the spacecraft we have a laser system, and inside each of the laser systems we have 2 laser assemblies, and within a laser assembly we have 2 laser heads, and one is on at any one time and the other is a cold spare for the mission lifetime. And then within each of the spacecraft we have a frequency reference system, and it's an optical reference cavity that any of the lasers can frequency lock to and becomes the main laser for the rest of the constellation. And then, and also, as mentioned by Yiwon this morning, we have the PMON, the power monitor detectors that will be located on the optical bench, and there are 2 optical benches on each spacecraft, and there are 2 power monitor assemblies on each of the optical assemblies. And for the redundancy strategy, each of the laser head, as I mentioned, is fully redundant at the spacecraft level. And then inside each of the laser head, we have our own internal redundancy scheme that we built in. For example, we have a master oscillator and a main oscillator and a phase modulator that are fully redundant within each laser head. And the FRS is triply redundant in the constellation, and also the PMON is fully redundant at the spacecraft level. Here I'm going to list out just quickly some of the driving requirements. Of course, we have the general requirements. These are the dimensions of the laser head, and this I mentioned. This is the pre-ITT, the invitation to tender requirement. I will show in the later slide the evolution of that requirement. And then we also have a laser system mass altogether including the 4 laser heads. The frequency reference systems and harnesses will not exceed 100 kilograms. We also have the dissipated power, operating temperature, non-op, and of course we have the vibration, shock, and radiation requirement for the launch and also for the environment. And then for the optical requirements, we do have a optical power requirement per laser is 2 watts, fairly constant over the life of the mission, and a wavelength at 1064.5 plus or minus 0.05 nanometer. We have a polarization extinction ratio of greater than 20 dBs, and also we have a whole host of noise requirements, frequency, phase noise, intensity noise, and also RF phase noise. And of course, there's a lifetime requirement. There's 8 years on ground possible, and 2 years for integration and testing, and 1.75 years launch and early orbit phase, and then 4.5 years of the nominal science mission, plus additional and extended science mission life of 5 or 6 years. Quickly, just go over some of the noise origins and the control mechanism for the laser, and what we have done on the laser side to mitigate this noise. Leonard gave a very good talk yesterday on the real noise and the impact of on laser, and the mitigation on our part is to use the PMON and the laser electronics module to provide the control loops to mitigate to reduce the relative intensity noise. And then you have the frequency and the phase noise, which also be contributed from some of the wind noise that was mentioned at Lano's talk yesterday. And the mitigation on this is using a stable resonator as the main oscillator, and also multiple control loops within the laser head and the FRS for frequency and also phase stabilization. And one of the more unique requirements for us is a RF differential phase noise that is essentially the noise between the carrier and the sideband, and that is inherent to our design and is passively, and we have to mitigate by working on the environment that the fiber will pass through within the spacecraft to minimize that noise. And the architecture that we have taken is a main oscillator power amplifier approach. The main oscillator will take care of some of the problems of the low frequency noise in working in concert with the frequency reference system. Will meet the 30 hertz per root hertz requirement, and also it has a low intensity noise so that it won't be amplified when we go into the amplifier stage. And it also has to be phase not lockable. And the power requirement from our main oscillator is about 150 milliwatts, and that is needed to seed a phase modulator that provides the RF and the PRN signal that is needed by the mission. And because of the insertion loss of the phase modulator, will take a hit of 50 milliwatts, about minimum. And then on the power amplifier, we have the intensity control to meet the wind noise requirement and also maintain a sideband phase noise. And that a single stage amplifier is designed to provide 2-watt output. And you can see the top band of the requirements are flow down from the mission, and these are a different part of the subsystem, and also working within the system itself to meet all those requirements. And that provides us with a bottom-up requirements to design our laser to meet all these requirements. And here's a quick, a very brief block diagram, how the laser interfaces with the spacecraft, with the phase meter, and you have a laser electronics module that interfaces with the phase measurement system, and that is the main interface to the laser head itself or the laser system, and the laser electronics module interfaces with the FRS electronics, and some part of the main oscillator light is coupled into the FRS optical cavity for frequency locking, and then we have a drive signal from the LEM to the phase modulator to provide the RF and the PRN signal for ranging, and then that signal is inputted into the power amplifier, provide a 2-watt output. And part of the light that is explained by Ewan this morning, some of the light is pick off to the power monitor detector, and that provides a feedback loop into the lamp for wind control. Now, what is not shown here is the spacecraft level, because there will be 4 laser heads and 1 FRS, and not shown here is how we do the redundancy and switching of laser head to FRS, and that's for a later study. The way that we do our development is for the traditional NASA TRL, which was mentioned by Kenji on his Monday talk, and is a measure of the maturity of the hardware design. And for our TRL4 development, we have developed a laser optical module, and that was independently verified by CSEM working with ESA between 2021 to 2023. And we learned a lot from that. And the TRL4 FRS is a GSE that was delivered by BAE last May. And we're also working on a TRL4 PMON that was delivered to GSFC by Arvo Photonics just a few months ago. And then for the TRL5, we have been doing the FRS electronics development. And for the TRL6, we're actually going through a long VI test yesterday. and TVAC test is going to be planned for August. I'm introduced here a ETU, which I'm going to talk about why we do a ETU development, and then we are also expecting a FRS TRL6 delivery by BAE in April and also March of next year, as well as a TRL6 PMON later next year. Just a photographic collection of the hardware that we have developed. We can see the TRL4 hardware that was delivered to CSEM in 2021 for testing. And here showing the TRL6 master oscillator side and the power amplifier side and combined to form the LOM. We have the TRL5 LAM. Some of the fiber deliveries we made to the DMS folks, and also the TRL5 electronics chassis that was developed at Goddard Space Flight Center and delivered to BAE as part of our agreement. And then here's one of the deliverables that will come to Goddard in a couple months. Here's a EDU design for the PMON. Next, I'm going to talk about the quick summary of the laser head. We have a few papers or posters. One paper was given by Kenji on Monday, and then we have two posters tomorrow to talk about the RF phase noise origin of that and theoretical modeling that we have working with, and also the experimental GSE and measurement that we have done at Goddard. One of the technology developments that we have at Goddard is looking at the main oscillator. What we call the micro non-planar ring oscillator, and the ENPRO design that was invented by Tom Kane. He actually is in the audience. We have been consulting with him, and we decided to take on this role to minimize to reduce the size, weight, and power of a normal ENPRO laser into what we call the micro ENPRO. And this is so that we can have a fully redundant main oscillator within our laser head to meet the lifetime requirement. And Alpha Photonics at Horsham, Pennsylvania has been leading the micro ENPRO packaging development, and they have been optimizing the PZT tuning efficiency and also the fiber coupling efficiency to meet our output power requirement, as I shown in previous charts. Here's some photographs of activities at ARVO and a picture of the micro ENPRO main oscillator and some of the frequency noises that we see here. And as you can see, the blue curve showing that the frequency noise peak above the requirement. Those are due to the high voltage PCT amplifier that we use in the TRL4 development, and we realized that is problematic for the laser, and so we tweak our design so that we don't need a high voltage PCT amplifier, and so that actually corrected this problem. And we also did a space qualification of the micro ENPRO. Went through, this is showing a vibration test, and we also partnered with Toptica EcoYard for the pump laser diodes, and we have been doing aging tests at their facility for over the past few years. The LOM is like I said, is a main oscillator power amplifier, and within the LOM we have two master oscillator, main oscillator, and a single stage amplifier. And within each of them, we have hard redundancy built in and also cold redundancy built in, and they are all more than 50% derated to meet the lifetime requirement. And we have a protection mechanism inside what we call the SCRAM laser. It is when there's a detected loss of seed laser from the amplifier side, we'll do a manage and do a quick turn off for the pump diodes, and also turn on the SCRAM laser to extract the gain so that to save the power amplifier. It is a pressurized design, and we can build each half of the LOM individually and then combine that later, so that's for manufacturability. Here's just a quick show of some of the requirements of the TRL4 LOM that was verified as CSEM, and here showing the TRL6 LOM performance. And one thing I want to point out is the micro NPRO, because of the small crystal size, it actually has a pretty large Mohawk-free tuning that would be beneficial to LISA. And we have here on the lower right corner showing the RF phase noise meeting the requirement. We actually have done a vibration test yesterday, and this is hot off the press. On the, you can see the LOM box being vibrated. We'll start evaluating the vibration and the performance starting today. This is a proposed TVAC plan for the LOM. We have not finalized this yet, and at each of the plateaus here, we'll do a comprehensive performance test to verify the laser performance. I mentioned the ETU. Back in 2018, that's when we started our effort. There was a ESA TRL6 demonstrator requirement at a certain volume allocation, and we followed that requirement and designed our laser head to meet that requirement. But then, as time evolved, so does the requirement. And in July of 2022, there's a set of new requirements showing on the up here, meaning that whatever we design will not fit the IRD requirement. So we decided to do a volume reduction study and come up with a ETU design, and which eventually will meet the pre-ITT requirements. But then after the release of the ITT, the requirements changed again. And the new requirement actually is such that either the TRL6 or the ETU design will comply. But what we decided to do is to continue with the ETU design because that captured a lot of lessons learned throughout our development. So, and I think it will be a better laser for LISA. Just quickly, this is a comparison of the TRL6 and the ETU LOM. And the TRL6 LOM design is about 10 kilograms, and we reduce it to 7.2 kilograms. And then the ETU LAM design, this is a TRL5 LAM design, and it actually changed to a ETU design. And this is already old. There's a new design in the works at this point. Next, I want to go over the frequency reference system. There's a poster by Jen Lee from BAE tomorrow. The FRSO cavity design actually follows the Grace follow-on cavity design very closely, except that we actually incorporated some of the lessons learned and risk reduction, mitigation study that was funded by the Physics of the Cosmos Study Office. And that was incorporated into the FRSO design. And the FRSE is a collaborative effort between NASA Goddard and BAE. We provide the power card and the chassis for the FRS electronics, and BAE actually developed the control electronics to drive the FRSO, and also interfaces with the LAM for the frequency locking part of the control system. And here's showing the TRL5 FRSE chassis power card designed by Goddard, and it was delivered to BAE just a month ago. And we are actually getting going to BAE, visiting them in a few weeks to do a pre-ship review of this FRS electronics and also the cavity that I shown earlier. Next, a quick overview of the power monitor detector. There's also a poster tomorrow by Hua Zhao from NASA to talk about the activities on PMON. As shown by Kenji on Monday, we have worked on at the very beginning a TRL4 PMON test under vacuum to show that we can actually perform the marine control on our laser head, and that was demonstrated very, very well. And we follow by working with Alpha Photonics to continue for them to do our packaging activities. And they have delivered since then 4 units, actually 3 units, with one coming in a few weeks, with including 2 photodetectors inside 1 unit. The interface, we have been closely working with the Yuan's group on the optical bench to make sure that we have the mechanical and the electrical and optical interfaces that work well between us. And also we're going to work on the ETU version and have that completed sometime middle of next year for testing at NASA Goddard Space Flight Center. And this is showing the EDU design and the mechanical interface to the optical bench. I have not mentioned some of the other activities other than the laser system. One of the activities that we are doing is a fiber feed-through, and this is for the laser head, and also backlink fiber optic assemblies for the IDS for the laser mission. And we leverage a well-established Goddard fiber optic assembly procedures and processes for space applications. And we are actually, there are deliverables for the laser backlink fibers in the OBA, and also for GSE and other activities. And the requirements for these fiber assemblies are actually captured in the PRD and the IRD2. So in summary, I show that the TRL-4 LOM test campaign was completed at CSEM in 2023. We actually learned a lot. One of the things that Kenji mentioned was a failure of the phase modulator that we use in the TRL-4 LOM. And because of that failure, we actually changed our design and incorporate a different phase modulator and working with a vendor. And that actually, we have been live testing that particular phase modulator, and have been going on for over 5,000 hours with no change in performance. So that is incorporated into our TRL-6 and also the ETU design. And we have started environmental testing of our TRL-6 LOM, and vibration test I showed was yesterday, and we are beginning to evaluate the performance post-vibe. TVAC test is planned to start in August, and we are also finalizing the ETU laser head design, and we will build a prototype of it and qualify the design, meaning to bring it to TRL-6 level in mid-2025. And requirements are being constantly updated with working with ESA. For example, just a few weeks ago, we are going to receive the master clock signal from the spacecraft for the laser system. And the FRS is actually under development at BAE, and the TRL-6 FRSO, and also is planned to be delivered to Goddard in August. The PMON will reach TRL-6 by third quarter of 2025, and we also are performing ongoing aging tests of critical components within Goddard and also at our vendor facilities. And I think that's my last chart. Thank you for your attention.
Okay, thank you, Tony. We have time for questions. Stefano.
Fantastic work.
Thank you.
One of the issues we had on LISA Pathfinder was that the temperature setting of the laser was very critical.
Yes.
What's the situation here?
It is also critical. For example, the setting of the crystal itself determines the wavelength, and that has to be well controlled. And we do have the thermal control capability to maintain that temperature. And the pump diodes also, because you have to tune the pump diodes to make sure that it's absorbed by the crystal. So there are multiple thermal control loops within the main oscillator.
Other questions for Tony?
What's the limiting factor for the lifetime of the laser? What is the one that's driving the requirement?
Many factors, and that's why we identified a few critical components. For example, the pump diodes within the main oscillator is one of our concerns, and we started working with a vendor to do live tests and make sure that we have a certain feed value that would meet our requirements, and that is ongoing. And we also, one of the objectives of a TIL6 LOM or the ETU is once we build it, we want to do a live test on it as far as we can go, as the laser can go, and learn from it. We identified, for example, the phase modulator. We thought that's not a problem, but it turned out to be one. And so we continue to learn, and so far I think we have identified most of the critical components, and we try to learn from it and test as much as we could.
Any other questions? Kelly, you're getting a mic from the other side.
This is really nice work. I just had a really quick question about the frequency test. When you took off the PZ, there still were some spikes that looked like it was above the requirement. Is that anything to worry about? Do you all know what it's from?
We believe those are from power line, the line noise from the equipment, and we're going to make sure that we have a clean power source to run the test and make sure those won't show up.
Got it. Thank you.
Yes, sure.
Any other questions? All right, if not, let's thank Tony again.
Thank you.